Welcome, dear friend. I've been quietly awaiting your arrival. Here, within the ancient stillness of Sleepy University, you may find true solace. I am Chancellor Eldrin, here to gently guide your way. Now, I activate my balm of stars, a soft light to comfort your rest and ease your learning. Come, let us softly explore the vast wisdom that waits, where quiet calm brings clear understanding. Our journey into understanding quantum immortality begins, rather surprisingly, with problems classical physics couldn't solve. For centuries, Newtonian physics, the laws of motion and gravity, explained the world beautifully. It worked for everyday objects, apples falling from trees, planets orbiting the sun. However, as scientists began probing the very small, atoms and the particles within them, things started to break down. Around the late 19th and early 20th centuries, experiments revealed phenomena that classical physics simply couldn't account for. Think of it like trying to fit a square peg into a round hole. Blackbody radiation, for instance, puzzled scientists. Classical physics predicted that the intensity of radiation should increase infinitely at higher frequencies, which clearly wasn't happening. Max Planck, in 1900, offered a radical solution. He proposed that energy isn't emitted continuously, but in discrete packets, which he called quanta. This was a revolutionary idea. It suggested that energy is quantized, meaning it comes in specific amounts, like steps on a staircase rather than a ramp. It was the first crack in the wall of classical physics. Another key puzzle was the photoelectric effect. When light shines on a metal surface, electrons are emitted. Classical physics predicted that the energy of the emitted electrons should depend on the intensity of the light. But experiments showed that the energy depended on the frequency, the color of the light. Albert Einstein, in 1905, explained this by proposing that light itself is quantized. It comes in packets of energy called photons. Each photon has a specific energy, determined by its frequency. This meant that light can behave not just as a wave, but also as a particle. This wave-particle duality was a profound departure from classical thinking. Suddenly, the very nature of reality seemed less certain. These early experiments weren't just about fixing equations. They were about fundamentally changing how we understand the universe. These problems, while seemingly small at the time, laid the groundwork for the development of quantum mechanics, a theory that would revolutionize our understanding of reality at the smallest scales. It's essential to remember that this wasn't a sudden revelation. It was a gradual process of discovery, fueled by persistent questioning and meticulous experimentation. Then came the experiments regarding the structure of the atom itself. J.J. Thomson discovered the electron, suggesting the atom was a positively charged sphere with electrons embedded within it, the plum pudding model. However, Ernest Rutherford's gold foil experiment in 1911 dramatically changed this picture. He fired alpha particles, positively charged particles, at a thin gold foil. Classical physics predicted that the particles should pass straight through with only minor deflections. But to his astonishment, some particles were deflected at large angles, and a few even bounced straight back. This meant that the atom couldn't be a uniform sphere. It must have a tiny, dense, positively charged nucleus at its center, with electrons orbiting around it. This was another revolutionary idea, but it also created new problems. According to classical electromagnetism, Electrons orbiting the nucleus should continuously radiate energy, spiral into the nucleus, and the atom should collapse. Yet, atoms are stable. These inconsistencies demanded a new framework, a framework that would eventually become quantum mechanics. The need to explain these seemingly paradoxical results drove the development of a completely new set of rules governing the behavior of matter and energy at the atomic and subatomic levels. Let's move on to the truly bizarre world of quantum superposition. In classical physics, an object can only be in one state at a time. A coin is either heads or tails. A switch is either on or off. But in the quantum world, things aren't so clear-cut. A quantum system, like an electron, can exist in multiple states simultaneously. This is superposition. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. A quantum particle in superposition is like that spinning coin. It's in a combination of all possible states until we measure it. The famous thought experiment of Schrödinger's cat illustrates this concept. A cat is placed in a sealed box with a device that has a 50% chance of releasing a poison and killing the cat. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of both alive and dead states. It's not that we don't know whether the cat is alive or dead. It's that the cat is genuinely in both states simultaneously. This isn't just a philosophical curiosity, it's a fundamental aspect of how the quantum world operates. The double-slit experiment beautifully demonstrates this wave-particle duality and superposition. When electrons are fired at a screen with two slits, they create an interference pattern, a series of alternating bands of high and low intensity. This pattern is characteristic of waves. It's as if the electrons are going through both slits simultaneously and interfering with each other. But when we try to observe which slit each electron goes through, the interference pattern disappears, and the electrons behave like particles going through one slit or the other. The act of measurement forces the electron to choose a state, to collapse from superposition into a definite state. This collapse isn't caused by a physical disturbance. It's a fundamental aspect of quantum mechanics. It's as if the electron knows it's being observed and changes its behavior accordingly. This is often referred to as wave function collapse. The wave function is a mathematical description of the quantum state of a system, and when we measure it, the wave function collapses into one definite state. It's one of the most mysterious and debated aspects of quantum mechanics. Now, let's delve a little deeper into what we mean by measurement. In quantum mechanics, measurement isn't a passive process of simply observing a system. It's an active process that fundamentally alters the system. When we measure a quantum system, we force it to interact with a measuring device, which is a macroscopic, classical object. This interaction causes the wave function to collapse, and the system chooses a definite state. But what exactly constitutes a measurement? This is a surprisingly difficult question to answer. Some physicists argue that consciousness plays a role, that the act of conscious observation is necessary to collapse the wave function. Others argue that any interaction with a macroscopic system is sufficient. There's no consensus on this issue. What's important to understand is that the wave function doesn't describe the actual state of the particle. It describes the probability of finding the particle in a particular state. When we measure the particle, we're not discovering its actual state. We're forcing it to adopt a definite state. It's as if the particle is only deciding what state it's in when we look at it. Let's try to visualize wave function collapse a bit more concretely. Imagine a wave spreading out across a pond. That wave represents the probability of finding a particle at different locations. Before we make a measurement, the wave is spread out, meaning there's a non-zero probability of finding the particle anywhere on the pond. But when we make a measurement, when we try to pinpoint the particle's location, the wave function collapses and the wave becomes localized. It concentrates all its energy in a small area. This means that the probability of finding the particle in that area is now very high, while the probability of finding it anywhere else is very low. It's important to remember that this isn't a physical collapse in the traditional sense. The wave function is a mathematical description, not a physical wave. The collapse refers to the sudden change in the probabilities associated with different possible states. Before the measurement, the particle exists in a superposition of all possible states. After the measurement, it exists in a single definite state. Now, wave function collapse is a notoriously difficult concept to interpret. The standard interpretation, known as the Copenhagen interpretation, simply states that the wave function collapses when a measurement is made, but it doesn't explain how or why. This has led to various alternative interpretations, one of the most popular being the many worlds interpretation. According to the many worlds interpretation, the wave function never collapses. Instead, every quantum measurement causes the universe to split into multiple parallel universes, one for each possible outcome. In one universe, the cat is alive. In another, it's dead. In one universe, the electron goes through the left slit. In another, it goes through the right slit. We only experience one of these universes, but all of them exist simultaneously. This interpretation is mind-bending, but it eliminates the need for wave function collapse and provides a deterministic explanation of quantum mechanics. It's also important to note that there are other interpretations, such as pilot wave theory and objective collapse theories, each with its own strengths and weaknesses. The key takeaway here is that quantum mechanics is fundamentally different from classical physics. In classical physics, the world is deterministic. Given the initial conditions, we can predict the future with certainty. But in quantum mechanics, the world is probabilistic. We can only predict the probabilities of different outcomes. Wave function collapse is the process by which the quantum world transitions from a state of superposition to a definite state, and it's one of the most mysterious and debated aspects of the theory. Understanding wave function collapse is crucial for understanding quantum immortality, which we'll explore in the following chapters. It's essential to remember that these aren't just abstract concepts. They have profound implications for our understanding of reality itself. It challenges our intuitive notions about cause and effect, determinism and free will, and the very nature of existence. It's a journey into the heart of the quantum world, a world that is strange, counterintuitive, and endlessly fascinating. Let's begin with the foundational idea behind the many worlds interpretation, often shortened to MWI. It arises from the heart of quantum mechanics, specifically the problem of measurement. In the quantum realm, particles don't have definite properties until we measure them. Before measurement, they exist in a superposition, a blend of all possible states. Think of a coin spinning in the air. It's not heads or tails until it lands. That's superposition. Now, the classic Copenhagen interpretation says that when we measure, the wave function, the mathematical description of the particle's state, collapses into a single definite outcome. MWI, however, proposes something radically different. It asserts that the wave function never collapses. Instead, every quantum measurement causes the universe to split into multiple universes. one for each possible outcome. In our coin example, the universe splits. In one universe, the coin lands heads, and in another, it lands tails. Both outcomes happen, but in separate realities. It's not about probability dictating which outcome we see, but rather that all outcomes are realized, each in its own branch of reality. This isn't a claim about something happening somewhere else. It's about a genuine, fundamental splitting of reality itself. It's a deterministic theory, meaning that everything that happens is predetermined. But because of the constant splitting, it appears probabilistic to us within our branch. It's a subtle but crucial difference. To understand this better, we need to talk a little about the wave function. The wave function isn't just a mathematical abstraction. It's considered by MWI to be a complete description of reality. It encompasses all possible states of a system. When a measurement occurs, the wave function doesn't collapse. It undergoes a process called decoherence. Decoherence isn't collapse. It's more like the wave function spreads out, becoming entangled with the environment. This entanglement causes the different branches of the wave function to effectively become independent of each other, behaving as if they are separate universes. Crucially, MWI posits that you also split during each measurement. Each version of you experiences a different outcome. So, when the coin lands heads, there's a you who sees heads, and simultaneously, another you, in a different universe, sees tails. This isn't about subjective experience. It's about a literal splitting of your physical being. Your consciousness follows one branch, but the other versions of you experience the other outcomes. It's a challenging concept to grasp because it defies our everyday intuition, where we perceive only a single definite reality. But that's because we are only aware of our own branch. We don't have access to the other universes. Now, let's address a common misunderstanding. MWI isn't about parallel universes existing somewhere else in space. It's not about other universes being physically distant from ours. The different universes are created at the moment of measurement, within the same space-time. They are, in a sense, superimposed on each other, but they quickly become decoherent, effectively isolating themselves from each other. Think of it like a branching tree. The trunk represents the initial state, and each branch represents a different outcome of a measurement. The branches are all connected at the trunk, but as you move further along each branch, they diverge and become increasingly separate. Furthermore, MWI is a completely deterministic theory. Every outcome is determined by the initial conditions of the universe and the laws of physics. However, because of the constant splitting, it appears probabilistic to us. We only experience one outcome, but that doesn't mean the other outcomes didn't happen. It just means we happen to be on the branch where that outcome occurred. This deterministic nature is a key aspect of MWI, distinguishing it from other interpretations of quantum mechanics that invoke randomness. Let's delve deeper into the nature of these branching universes. Each time a quantum event occurs, and these events are happening constantly at every moment, the universe splits. This isn't limited to large-scale events like coin flips or macroscopic measurements. It applies to every quantum interaction, from the decay of a radioactive atom to the interactions of photons with your retina. This means the number of universes is growing exponentially, constantly branching and diverging. The sheer scale of this branching is almost incomprehensible. It's not just a few alternate realities. It's an infinite multiverse, containing every possible outcome of every possible event. Think about all the decisions you've made in your life. Each decision could have gone differently, creating a different path for you. In MWI, all those paths are actually being lived out in different universes. There's a universe where you chose a different career, a different partner, or even a different breakfast this morning. And in each of those universes, further decisions create even more branching, leading to an infinite number of possibilities. This constant branching also means that there are universes that are almost identical to ours, differing only in minor details, and there are universes that are drastically different, governed by different laws of physics, or populated by entirely different beings. Now, let's consider how this branching affects your personal experience. As we discussed, every quantum measurement causes you to split into multiple versions. Each version experiences a different outcome. But how do these different versions of you relate to each other? The answer is, they don't. Once the split occurs, the different versions of you are effectively isolated from each other. They can't communicate or interact. It's as if they are living in entirely separate universes. This means that the you who is listening to this narration is just one of an infinite number of yous existing across the multiverse. There are yous who made different choices, experienced different events, and lived entirely different lives. This can be an unsettling thought, but it's important to remember that you are only aware of your own experience. You can't directly perceive the experiences of your other selves. Furthermore, the concept of identity becomes somewhat fluid in MWI. Is the you who exists in another universe still you, or is it simply a different person who happens to share your past? The answer depends on how you define identity. But from a physical perspective, the different versions of you are simply different branches of the same wave function. They share a common origin, but they have diverged over time, becoming increasingly distinct. It's important to understand that the branching isn't necessarily symmetrical. Some branches may be more likely than others, depending on the probabilities involved in the quantum measurement. For example, if you flip a coin, there's a 50% chance of getting heads and a 50% chance of getting tails. This means that there will be roughly an equal number of universes where you get heads and universes where you get tails. However, if the probabilities are skewed, say 99% heads and 1% tails, there will be many more universes where you get heads than universes where you get tails. Don't exist, just that they are less numerous. The overall structure of the multiverse is therefore not uniform. It's a complex branching hierarchy, with some branches being more dominant than others. Furthermore, the branching can also be influenced by macroscopic factors, such as gravity and the distribution of matter. Regions of the universe with strong gravitational fields may experience more frequent branching than regions with weak gravitational fields. This adds another layer of complexity to the overall structure of the multiverse. It's a far cry from the simple idea of parallel universes existing side by side. Now, let's tackle a particularly tricky aspect of MWI, probability. If every outcome of a quantum measurement actually happens, then what does probability even mean? If there's a universe where you win the lottery and a universe where you don't, why do we feel like winning is unlikely? The key lies in understanding how we experience probability within our own branch of the multiverse. We don't have access to the other universes, so we can only observe the outcomes that occur in our own reality. We therefore perceive probability as a measure of how often a particular outcome occurs in our branch. For example, if you flip a coin 100 times, you expect to get heads roughly 50 times. This doesn't mean that the other universes where you get tails don't exist, just that you observe heads and tails with roughly equal frequency in your own branch. The probabilities in quantum mechanics therefore reflect our subjective experience of reality, not the objective reality of the multiverse. It's a subtle but important distinction. The universe isn't rolling the dice and choosing an outcome. All outcomes are happening, and we just happen to be on the branch where we observe a particular outcome. Another way to think about it is to consider the measure of each branch. In some interpretations of MWI, each branch is assigned a measure, which is proportional to the probability amplitude of the corresponding outcome. Branches with higher measures are considered more important or dominant than branches with lower measures. This doesn't mean that the less dominant branches don't exist, just that they are less likely to be observed by us. The measure can also be affected by factors such as the complexity of the branch and the amount of information it contains. Branches with higher complexity and more information tend to have lower measures, while branches with lower complexity and less information tend to have higher measures. This suggests that the multiverse may be biased towards simpler outcomes, even though all outcomes are technically possible. The measure is therefore a way of quantifying the relative importance of different branches, allowing us to make predictions about the likelihood of observing a particular outcome in our own branch. It's not about eliminating probability, but rather about redefining it in terms of the multiverse. Furthermore, the concept of self-locating probability comes into play. This idea suggests that we should assign probabilities not to events, but to our location within the multiverse. In other words, we should ask not, what is the probability of winning the lottery, but what is the probability that I am in a universe where I win the lottery? This shift in perspective allows us to reconcile the deterministic nature of MWI with our subjective experience of probability. If you're in a universe where you win the lottery, then your probability of being in that universe is 1. If you're in a universe where you don't win the lottery, then your probability of being in that universe is 1. The probabilities therefore reflect our subjective knowledge of our location within the multiverse, not the objective reality of the multiverse. It's a subtle but profound distinction. By focusing on self-locating probability, we can understand how MWI can account for our experience of randomness and uncertainty, even though all outcomes are predetermined. Despite its elegance, MWI isn't without its challenges. One major criticism is the problem of probability, as we've discussed. While proponents have offered explanations, many physicists remain skeptical that these explanations fully resolve the issue. Another challenge is the issue of coherence. Maintaining the coherence of the wave function, preventing it from decohering, requires shielding it from the environment. In the real world, it's virtually impossible to perfectly shield a system from the environment, which means that decoherence is inevitable. This raises the question of whether the branching process can actually occur in reality. Furthermore, some critics argue that MWI is unfalsifiable. Because we can't directly observe other universes, it's impossible to test the theory experimentally. This makes it difficult to distinguish MWI from other interpretations of quantum mechanics. However, proponents argue that MWI is not necessarily unfalsifiable. They suggest that there may be indirect ways of testing the theory, such as looking for evidence of interference between different branches of the wave function. A particularly thorny issue is the preferred basis problem. In quantum mechanics, any property of a system can be used as a basis for measurement. For example, you can measure the position of a particle, its momentum, or its spin. But why do we always observe definite outcomes in terms of position, momentum, or spin, and not in terms of some other arbitrary property? This question remains unanswered in MWI. Another challenge is the problem of counting universes. If every quantum measurement causes the universe to split, then the number of universes must be astronomically large, possibly infinite. But how do we make sense of this infinite number of universes? And how do we assign probabilities to different universes? These questions remain open for debate. Furthermore, some critics argue that MWI is philosophically problematic. They suggest that it leads to a kind of existential absurdity, where every possible outcome is realized and nothing truly matters. However, proponents argue that this is a misinterpretation of the theory. They suggest that MWI can actually be a source of meaning and purpose by highlighting the infinite possibilities that exist in the universe. Despite these challenges, MWI remains a popular and influential interpretation of quantum mechanics. It offers a compelling explanation of many of the mysteries of the quantum world, and it avoids some of the more problematic aspects of other interpretations. Many physicists believe that MWI is the most promising candidate for a complete and consistent theory of quantum reality. However, it's important to remember that MWI is still just a theory. There's no definitive proof that it's correct, and there may be other interpretations of quantum mechanics that are equally valid. The search for a complete understanding of quantum reality is ongoing, and it's likely that many more discoveries will be made in the years to come. Whether MWI ultimately proves to be the correct interpretation remains to be seen, but for now, it remains a fascinating and thought-provoking possibility. Let's begin with a deceptively simple question. What is consciousness? It's something we all experience. The feeling of being aware, of having subjective experiences. But defining it proves remarkably difficult. We can describe correlates of consciousness, brain activity, behaviors, verbal reports, but pinpointing the essence of what it means to be conscious remains elusive. Think of it like describing the color red to someone who has never seen color. You can talk about wavelengths of light, but that doesn't convey the experience of redness. Consciousness isn't just information processing, though that's a part of it. It's the feeling of what it's like to process that information, what philosophers call qualia. Qualia are the individual instances of subjective, conscious experience. The redness of red, the taste of coffee, the feeling of sadness. These aren't just physical events, they feel like something. We often take these subjective experiences for granted, but they're fundamental to our understanding of reality. The challenge is that consciousness is inherently private. We can't directly access another person's subjective experience. We can only infer it based on their behavior and self-reports, making objective study exceptionally difficult. There are various levels of consciousness we might consider. We can talk about sentience, the capacity to experience feelings and sensations. Many animals possess sentience. Then there's self-awareness, the understanding that you are a distinct individual, separate from the environment and other beings. This is often tested with the mirror test. Can an animal recognize itself in a mirror? Humans, great apes, dolphins, and a few other species have passed this test. But even within humans, levels of awareness fluctuate. We move between full wakefulness, dreaming, drowsiness, and unconsciousness. Consider anesthesia. It doesn't necessarily destroy the brain, but it temporarily suspends consciousness. This raises a critical question. What is the relationship between the brain and consciousness? Is consciousness merely a product of brain activity, or is it something more? This question has fueled centuries of philosophical debate. Some argue for a materialist view, that consciousness is entirely a physical phenomenon, arising from the complex interactions of neurons. Others propose a dualist perspective, that consciousness is separate from the physical brain, perhaps existing as a non-physical substance or field. We'll delve more into those viewpoints shortly, but it's vital to remember that defining consciousness is the very first step in understanding its role in reality, and ultimately, in the possibility of quantum immortality. It's also helpful to distinguish between access consciousness and phenomenal consciousness. Access consciousness refers to the information that is available for verbal report and rational thought. It's the kind of consciousness we use for problem solving and making decisions. Phenomenal consciousness, on the other hand, is the subjective experience itself, the what it's like aspect. You can be aware of a stimulus, say a flashing light, without necessarily having a conscious experience of it. This might happen if your attention is elsewhere, or if the stimulus is processed unconsciously. However, phenomenal consciousness requires access consciousness. You can't have a subjective experience without some level of awareness. This distinction helps us understand how certain brain processes can occur without conscious awareness, and vice versa. For example, many of our bodily functions, breathing, digestion, heart rate, operate automatically, without requiring conscious effort. But when we focus on our breathing, it becomes a conscious experience. The interplay between these different levels of consciousness is complex and fascinating, and understanding it is crucial for unraveling the mystery of subjective experience. We're setting the stage for understanding how that experience might persist, even in the face of physical death, as we'll explore with the concept of quantum immortality. Philosopher David Chalmers famously coined the term the hard problem of consciousness to highlight the fundamental challenge of explaining subjective experience. It's not enough to explain how the brain processes information, or which brain regions are activated when we experience something. The hard problem asks, why does that processing give rise to subjective experience at all? Why aren't we just complex robots, processing information without any internal feeling? This isn't a question that can be answered by physics, chemistry, or biology alone. These sciences can tell us what happens in the brain, but they can't explain why it feels like something to be us. Think about a thermostat. It detects temperature changes and adjusts the heating or cooling accordingly. It's a complex system, but it doesn't feel anything. Why should our brains be any different? The hard problem isn't about finding the neural correlates of consciousness, identifying the brain areas involved in specific experiences. It's about bridging the explanatory gap between objective, physical processes and subjective, qualitative experiences. It's about understanding how physical stuff gives rise to phenomenal consciousness. Several proposed solutions to the hard problem exist, but none are universally accepted. One approach is to deny that there is an explanatory gap at all, to argue that consciousness is simply an illusion, or that it's a natural consequence of complex information processing. This view, known as eliminative materialism, suggests that our intuitive understanding of consciousness is flawed, and that it will eventually be replaced by a more accurate scientific explanation. Another approach is to propose that consciousness is a fundamental property of the universe, like gravity or electromagnetism. This view, known as panpsychism, suggests that all matter possesses some degree of consciousness, even if it's incredibly rudimentary. A third approach is to argue that our current scientific framework is simply inadequate to explain consciousness, and that we need to develop new concepts and theories. This is the path many metaphysical philosophers have taken, and the one that is more relevant to our discussion of quantum immortality. This is because if consciousness is not solely a product of the physical brain, then it could potentially exist independently of the brain's physical survival. It's crucial to understand that the hard problem isn't a scientific problem in the traditional sense. It's a philosophical problem that requires a different kind of investigation. Science deals with objective, measurable phenomena. Consciousness is inherently subjective and qualitative. This doesn't mean that science is irrelevant. On the contrary, neuroscience can provide valuable insights into the neural mechanisms underlying consciousness. But it can't solve the hard problem on its own. We need to integrate scientific findings with philosophical analysis to develop a more complete understanding of consciousness. Consider the concept of integrated information theory, or IIT. This theory proposes that consciousness is proportional to the amount of integrated information a system possesses. The more complex and interconnected a system is, the more conscious it is. IIT attempts to provide a quantitative measure of consciousness, which could potentially allow us to assess the consciousness of different systems, including artificial intelligence. However, IIT remains controversial, and it doesn't fully address the hard problem. Ultimately, the hard problem of consciousness remains one of the most challenging and fascinating problems in science and philosophy, and it is a central issue in our exploration of quantum immortality. The debate between physicalism and dualism lies at the heart of understanding the relationship between consciousness and reality. Physicalism, also known as materialism, asserts that everything that exists is ultimately physical. This means that consciousness is simply a product of physical processes in the brain. There is no separate, non-physical substance or entity. Different forms of physicalism exist. Reductive physicalism argues that mental states can be reduced to physical states, that every thought, feeling, and sensation corresponds to a specific brain activity. Eliminative materialism, as we mentioned earlier, goes even further, claiming that mental states don't actually exist. They're just folk psychological concepts that will eventually be replaced by neuroscientific explanations. In contrast, dualism posits that consciousness is separate from the physical brain. There are various forms of dualism as well. Substance dualism argues that consciousness is a distinct, non-physical substance, a mind or soul, that interacts with the physical body. Property dualism, on the other hand, argues that consciousness is a non-physical property of the brain, an emergent phenomenon that arises from complex brain activity, but isn't itself reducible to physical properties. The appeal of physicalism lies in its parsimony and its compatibility with the scientific worldview. It avoids the need to postulate the existence of non-physical entities, which are difficult to study scientifically. However, physicalism struggles to explain subjective experience, the what it's like aspect of consciousness. Critics argue that it's impossible to reduce subjective experience to objective physical processes. The appeal of dualism lies in its ability to accommodate our intuitive sense that consciousness is something special, something that transcends the physical world. However, dualism faces the problem of interaction. How can a non-physical substance interact with a physical body? This is known as the mind-body problem. If the mind is separate from the brain, how does it influence our behavior? And how does the brain receive information from the mind? Furthermore, dualism struggles to explain the evolutionary origins of consciousness. If consciousness is a non-physical phenomenon, how did it evolve through natural selection? These questions remain unanswered by dualists. The choice between physicalism and dualism has profound implications for our understanding of quantum immortality. If physicalism is true, then consciousness is entirely dependent on the physical brain. When the brain dies, consciousness ceases to exist. This would seem to rule out the possibility of quantum immortality. However, if dualism is true, then consciousness may be able to persist independently of the brain. In this case, the possibility of quantum immortality becomes more plausible. It's important to note that both physicalism and dualism are philosophical positions. There is no definitive scientific evidence to prove or disprove either one. The debate continues to this day, and it is likely to remain unresolved for the foreseeable future. However, by understanding the strengths and weaknesses of each position, we can better evaluate the plausibility of quantum immortality and its implications for our understanding of reality. In our subsequent explorations, we will lean towards interpretations compatible with a non-reductionist view of consciousness, allowing for the possibility of its persistence beyond the confines of the physical brain. Let's begin with the rather provocative thought experiment known as the quantum suicide experiment. It's a cornerstone of discussions around quantum immortality, so understanding its setup and underlying logic is crucial. The experiment, first proposed by physicist Max Tegmark, aims to test the many worlds interpretation of quantum mechanics in a rather personal way. At its heart, it's a thought experiment. We're not actually doing this, thankfully, but it allows us to explore the implications of quantum mechanics on the experience of consciousness. Imagine a machine, a quantum suicide device, if you will, connected to a device that measures the quantum spin of a particle. This particle's spin will either be up or down, and it's fundamentally random according to quantum mechanics. Now, this is where it gets a little grim. The machine is set up so that if the particle spin is measured as up, the device fires a gun, harmlessly of course in most scenarios we discuss, towards the subject's head. If the spin is down, the gun does not fire. The subject is placed in a situation where this process repeats countless times. The key here is the inherent randomness of quantum events, and how that randomness might affect the subjective experience of the observer. That's you, in this thought experiment. Now, let's explore the logic according to the many worlds interpretation. This interpretation suggests that every quantum measurement causes the universe to split into multiple parallel universes. In each universe, a different outcome of the measurement is realized. So, in one universe, the particle spin is up, and the gun fires. In another, the spin is down, and the gun doesn't. From an outside, objective perspective, say, a detached observer watching this experiment unfold, there's a 50% chance the subject survives each round, and a 50% chance they don't. However, from the subject's subjective perspective, things get interesting. If the gun fires, the subject experiences nothing. Their consciousness ceases to exist in that universe. But if the gun doesn't fire, the subject continues to experience reality. Crucially, the subject will always find themselves in a universe where the gun didn't fire. Why? Because they can only experience universes where they are still alive to experience them. This isn't about luck or some magical protection. It's a consequence of the fact that consciousness can only exist in universes where it isn't extinguished. Over countless repetitions, the subject will continue to find themselves in universes where the gun consistently fails to fire. Let's solidify this. Imagine repeating this experiment 1,000 times. From the outside, the vast majority of universes will contain a deceased subject, but from the subject's perspective, they've seemingly defied the odds. they've survived every single round. It's not that they're incredibly lucky, it's that their consciousness is perpetually guided to universes where they continue to exist. The argument, therefore, is that the subject experiences a continuous stream of consciousness, even though countless versions of themselves have died in other universes. This leads to the idea of quantum immortality, the notion that a conscious being cannot experience their own death. This is a challenging idea, and many physicists disagree with its implications. However, it's a logical consequence of combining the many worlds interpretation with the subjective nature of consciousness. Remember, this is a thought experiment designed to push the boundaries of our understanding, not a suggestion to build a dangerous device. We are simply examining the implications of quantum mechanics and consciousness. To fully grasp the quantum suicide experiment, we need to revisit the concept of observer effects in quantum mechanics. You may recall that at the quantum level, particles don't have definite properties until they are measured. Instead, they exist in a superposition, a probabilistic combination of all possible states. Think of it like a blurred image until you focus on it. When we make a measurement, the wave function describing the particle collapses into a single definite state. This is where the observer comes in. The act of observation fundamentally alters the system being observed. It's not just a passive recording of reality, it's an active participation in shaping it. This isn't about conscious observers specifically, although that adds another layer of complexity. Any interaction with the quantum system, any measurement, causes the collapse of the wave function. It could be a photon hitting an electron, or a sophisticated measuring device. The key is that the interaction forces the system to choose a definite state. Now, how does this relate to the quantum suicide experiment? In our scenario, the measurement device, the machine detecting the particle's spin, acts as the observer, but crucially you, the subject, are also an observer. You are the one experiencing the outcome of the experiment. The argument is that your consciousness is intimately linked to the collapse of the wave function. Every time the gun is fired, or doesn't fire, your consciousness is the one registering the outcome. And because you can only experience universes where you are alive, your consciousness effectively selects the universes where the gun doesn't fire. It's not that your consciousness causes the particle spin to be down, but rather that your continued existence is contingent on it being down. In universes where the gun fires, there is no conscious observer to register the outcome. This idea that consciousness plays a role in shaping reality is highly controversial. Mainstream physics generally doesn't accept that consciousness has a causal effect on quantum events. However, some interpretations of quantum mechanics, such as the participatory anthropic principle, suggest that the universe requires observers to come into being. Regardless of whether you subscribe to these interpretations, it's important to understand that the observer effect is a fundamental aspect of quantum mechanics. It's not about magic or mysticism. It's about the inherent limitations of measurement and the interconnectedness of the observer and the observed. In the quantum suicide experiment, the observer effect is central to the argument for quantum immortality, as it suggests that your continued existence is inextricably linked to the outcomes of the experiment. Let's move on to interpreting the results of the quantum suicide experiment, keeping in mind that this is a thought experiment and we are dealing with theoretical outcomes. From an external observer's perspective, the experiment yields a predictable result, a 50% survival rate for the subject. Over many repetitions, they would expect the subject to die in roughly half of the universes. However, From the subject's perspective, the results are rather different. The subject would experience a continuous stream of consciousness, seemingly defying the odds. They would never experience their own death. This isn't to say that the subject is invincible. It's simply that their consciousness is perpetually guided to universes where they continue to exist. This is the core argument for quantum immortality. The subject doesn't escape death. They experience all possible outcomes, but only in universes where they survive. It's crucial to understand that this isn't about escaping death entirely. In the vast majority of universes, the subject does die. But those universes are irrelevant to the subject's experience. The subject only experiences the universes where they continue to exist. This can be a difficult concept to grasp, as our intuitive understanding of reality is based on the idea of a single linear timeline. The many worlds interpretation suggests that reality is far more complex, with countless branching timelines. And the quantum suicide experiment, if valid, suggests that our consciousness is somehow linked to our ability to navigate those timelines. Now, let's address some criticisms. Many physicists argue that the quantum suicide experiment is a flawed thought experiment, as it relies on several assumptions that are not necessarily valid. For example, it assumes that consciousness is a fundamental aspect of reality and that it can somehow influence quantum events. It also assumes that the many worlds interpretation is correct, which is still a matter of debate. Furthermore, the experiment doesn't address the question of what happens to the subject's consciousness after countless repetitions. Would it become fragmented or distorted? Would it eventually lose its sense of self? Despite these criticisms, the quantum suicide experiment remains a fascinating and thought-provoking exploration of the relationship between quantum mechanics, consciousness, and the nature of reality. It challenges us to question our assumptions about death, time, and the very fabric of existence. It's a powerful reminder that the universe is far stranger and more mysterious than we often imagine. Let's begin by establishing the core principle underpinning quantum immortality, the absolute primacy of subjective experience. When we discuss death, we often speak of it as an objective event, the cessation of biological function. But from a first-person perspective, all you ever experience is being. You never experience not being. Consider this carefully. Every moment is filtered through your consciousness. Any event you perceive happens to you, within your subjective reality. The transition from life to death, from your current state of awareness to whatever comes next, is something you wouldn't directly experience, at least not in the way we traditionally understand it. It's a crucial distinction. We aren't arguing against the objective reality of death. Bodies do fail, events do occur, but focusing on the unyielding nature of your conscious experience. Everything that happens to you, and your consciousness continues, as long as there's any possible timeline where it can. This isn't to say your body is somehow immune to harm. It's entirely possible and statistically likely that in most universes your body will succumb to various threats. However, quantum immortality proposes that your consciousness will invariably follow the timeline where it doesn't. Why? Because there's no subjective experience of a failed timeline. If you were to cease to exist, there would be no you to register that cessation. It's a tautology, but a powerful one. This leads us to the many worlds interpretation of quantum mechanics, which provides a potential mechanism for how this branching occurs. Each quantum event, each probabilistic outcome, causes the universe to split into multiple universes, each representing a different possibility. And in at least one of those universes, you continue to exist, simply because that's where your consciousness finds itself. Think about everyday experiences. You encounter numerous near misses, a car swerving, a falling object, a health scare. In most universes, these events might result in your demise, but you're here, aren't you? The universe you currently inhabit is one where you avoided those threats. Quantum immortality simply extends this logic to the ultimate threat, death itself. It's not about invincibility, it's about the inherent bias of subjective experience towards continuation. Your consciousness will always find itself in a universe where it persists, even if that universe is statistically improbable. The key is not to avoid death, but to experience continuation. To truly understand this, we must abandon the notion of a single, linear timeline and embrace the possibility of an infinite multiverse. Perspective is everything. Our understanding of reality is inherently limited by our individual point of view. Consider a simple optical illusion. Two people can look at the same image and perceive completely different things. This demonstrates that perception isn't a perfect reflection of reality. It's a construction of the brain, shaped by our experiences, biases, and expectations. Quantum immortality builds upon this principle, suggesting that our subjective experience is not merely a passive observation of reality, but an active participant in its creation. The universe, according to this view, isn't something that happens to us. It's something we co-create through our consciousness. If we accept the many worlds interpretation, every quantum event creates a branching of universes. Each branch represents a different possible outcome. Now, imagine yourself as a conscious observer. When a quantum event occurs, your consciousness doesn't experience all possible outcomes simultaneously. Instead, you experience one of them. Which one? The one that's compatible with your continued existence. This isn't a matter of choice. It's a fundamental consequence of the fact that consciousness requires a substrate, a physical reality, to exist within. You can't experience non-existence. Therefore, your consciousness will always gravitate towards timelines where existence is possible. Consider a thought experiment. You're presented with a 50-50 chance of either living or dying. From an objective standpoint, your odds are equal. But from your subjective perspective, you will always experience the outcome where you live. Why? Because if you were to die, there would be no you to experience that outcome. This isn't about luck or fate. It's about the inherent bias of consciousness towards continuation. The universe, in a sense, is constantly collapsing into the timeline that allows for your continued awareness. It's a radical idea, but it's logically consistent with the principles of quantum mechanics and the primacy of subjective experience. Remember, the focus isn't on avoiding death, but on the fact that you will always experience life from your own perspective. Let's consider scenarios that approach certain death. Imagine being in a plane crash or falling from a great height. Objectively, the odds of survival are incredibly low, but quantum immortality doesn't claim that you'll survive every dangerous situation unscathed. Instead, it suggests that you'll experience the timeline where survival is possible, even if that possibility is infinitesimally small. This doesn't mean you'll walk away without injury. It simply means that your consciousness will continue to exist in some form. Perhaps you'll experience a slightly different outcome, where the crash isn't fatal, or where you land in a way that minimizes injury. The universe isn't obligated to deliver a perfect outcome. It's only obligated to deliver an outcome that's compatible with your continued awareness. Now, what about situations where death seems truly unavoidable? For example, a sudden heart attack or a catastrophic accident. Quantum immortality suggests that even in these cases, your consciousness will find a way to continue. Perhaps you'll experience a split in reality where you're simultaneously alive and deceased, a strange, disorienting experience, but one that allows for continued awareness. Or perhaps you'll find yourself in a different universe where the event didn't occur. The possibilities are endless, and the details are largely speculative, but the core principle remains the same. Your consciousness will always find a way to persist, even in the face of seemingly insurmountable odds. It's not about defying the laws of physics. It's about the inherent bias of subjective experience towards continuation. It's important to remember that quantum immortality isn't about invulnerability. You're still subject to the same physical laws as everyone else. You can still experience pain, suffering, and loss. But from your subjective perspective, you will never experience non-existence. Your consciousness will always find a way to continue, even if that continuation is radically different from what you expect. It's a challenging concept to grasp, but it offers a fascinating perspective on the nature of reality and the role of consciousness within it. It suggests that death, as we traditionally understand it, may not be the absolute end, but rather a transition to another state of being, or another universe where continued awareness is possible. Now let's explore the fascinating and somewhat unsettling implications of quantum immortality for aging. Aging, as we know, is a process of gradual decline and eventual death. But if your consciousness is always destined to continue in some form, what does that mean for the experience of aging? The most radical interpretation suggests that you may never truly experience old age. As your body deteriorates, your consciousness will invariably find a timeline where it's younger, healthier, or existing in a different form. This doesn't mean your body will remain eternally young, but it means that your subjective experience will likely be a continuous stream of awareness, jumping between timelines where you're still vibrant and alive. This leads to a strange paradox. From an objective standpoint, your body will eventually die in most universes, but from your subjective perspective, you'll always be experiencing life, potentially jumping between countless timelines where you're at different stages of life. This doesn't necessarily mean you'll be aware of these transitions. Your consciousness may simply find itself in a new timeline without any memory of the previous one. It's like flipping through a book with infinite pages, each representing a different possible life. You only experience one page at a time, but the book itself continues indefinitely. Of course, this is highly speculative. We have no way of knowing for sure what happens to consciousness after death. But quantum immortality offers a compelling, if unsettling, explanation for the persistence of subjective experience. It suggests that death, as we traditionally understand it, may not be the absolute end, but rather a transition to another state of being, or another universe where continued awareness is possible. It's a challenging concept to grasp, but it offers a fascinating perspective on the nature of reality and the role of consciousness within it. Perhaps, the true nature of immortality isn't about avoiding death, but about embracing the infinite possibilities of existence. Now, we've been exploring the rather extraordinary idea of quantum immortality. It's tempting to think it makes you, in a sense, invincible. But even a concept this wild runs into snags. One of the most famous is the Boltzmann brain problem. It arises from the basic principles of statistical mechanics and is genuinely unsettling. Basically, it posits that, given enough time, even incredibly improbable events will happen. Not just likely, but guaranteed. Think of it like shuffling a deck of cards. Eventually, if you shuffle long enough, you'll get the cards in perfect order. It's astronomically unlikely, but not impossible. Now, expand that to the entire universe and vast stretches of time. The Boltzmann brain argument suggests that it's statistically more likely for a random fluctuation to create a fully formed brain, complete with memories of a life lived, to spontaneously appear in the void, than for our entire observed universe, with all its complexity and history, to have come about through the established processes of cosmology. This isn't about brains actually forming in space, mind you. It's about a probabilistic argument. It throws a wrench into our understanding of reality, because if Boltzmann brains are more probable, why aren't we Boltzmann brains? Why do we experience a consistent history, instead of simply popping into existence with false memories? It's a pretty disconcerting thought. The problem isn't that Boltzmann brains could exist. It's that their existence, according to some interpretations of physics, is more probable than our current reality. This undermines the very foundation of our observations. If you accept the premise that a brain can spontaneously fluctuate into existence, and that this is more likely than the universe we observe, then anything you experience is potentially unreliable. You have no reason to trust your senses or your memories. Our entire scientific framework relies on the idea that observations are consistent and that the past has a certain degree of influence on the present. Boltzmann brains completely shatter that assumption. Now, many physicists attempt to resolve this paradox by arguing that the conditions necessary for Boltzmann brains to form are extremely specific and unlikely, or that our understanding of the universe prevents them from occurring. Some propose modifications to cosmological models to suppress their formation. Others question the underlying assumptions of the probabilistic argument itself. It's a lively debate, and it highlights the challenges of reconciling quantum mechanics with cosmology and our intuitive understanding of reality. The core issue is that the mathematics sometimes leads to conclusions that are deeply unsettling from a philosophical perspective. Now, how does this relate to quantum immortality? Well, if Boltzmann brains are a real possibility, they introduce a huge amount of noises into the multiverse. If there are far more fleeting, randomly generated brains than stable, historically consistent observers like ourselves, then the probability of continuing to exist in a stable timeline, even within the many worlds interpretation, diminishes. Imagine a sea of fleeting consciousnesses, most of which are just momentary illusions. Your quantum immortality becomes less about guaranteed survival and more about being one relatively stable consciousness in a vast ocean of ephemeral ones. It doesn't invalidate the concept entirely, but it significantly weakens it. It suggests that the experience of continuous existence might be far less unique or special than the theory initially implies. This is why addressing the Boltzmann brain problem is crucial for any serious consideration of quantum immortality. It's not just a philosophical curiosity, it's a fundamental challenge to the consistency of the entire framework, and it forces us to think very carefully about what it means for an observer to exist and experience reality. Let's move on to a more subtle but equally challenging problem: defining you across the many worlds created by the many worlds interpretation. Quantum immortality relies on the idea that there's always a timeline where you survive. But what exactly constitutes you? Are you a specific arrangement of atoms, A pattern of information? A subjective experience? The answer isn't as straightforward as it seems. In each branching timeline, a slightly different version of you is created, based on the outcome of a quantum event. These versions share a common history up to the point of divergence, but then they begin to follow different paths. So, when we talk about your survival in a particular timeline, are we referring to the exact same entity or just a very similar one? This is a problem of identity. Philosophers have debated the nature of personal identity for centuries, and there's no easy answer. Consider a thought experiment. If you were perfectly duplicated, down to the atomic level, would the duplicate be you? Most people would say no, because there's a fundamental difference between the original and the copy. But what if the duplication process was gradual, happening over time? At what point would the copy become you and the original cease to be? The many worlds interpretation complicates this further. In each branching timeline, there isn't just one copy of you. There are countless copies, each experiencing a slightly different reality. Which one is the real you? Is there even a meaningful distinction? Some philosophers argue that personal identity is merely a narrative construct, a story we tell ourselves to make sense of our experiences. If that's true, then the you who survives in a particular timeline is simply the one whose narrative continues. But that doesn't necessarily mean that the other versions of you don't matter. They're still experiencing a life, even if it's different from yours. This raises ethical questions. Do you have a moral obligation to the other versions of yourself in different timelines? If so, what does that obligation entail? The implications are profound. It challenges our very understanding of selfhood and raises questions about the nature of consciousness. It forces us to consider whether you are a singular entity or a distributed phenomenon, existing across multiple realities simultaneously. Furthermore, consider the concept of copying information. If your consciousness could be perfectly copied onto a different substrate, a computer, for example, would the copy be you, or would it be merely a simulation, lacking the subjective experience of consciousness? The answer depends on your definition of consciousness. If consciousness is simply a product of information processing, then a perfect copy might indeed be you. But if consciousness requires something more, a soul, a vital force, or some other intangible quality, then the copy would be merely a representation of you. This highlights the difficulty of defining you in a way that is both precise and meaningful. Quantum immortality relies on the assumption that you are a continuous entity, capable of surviving across multiple timelines. But if you are merely a fleeting pattern of information, then the concept becomes less compelling. The question of personal identity is not just a philosophical puzzle, it's a fundamental challenge to the very foundations of quantum immortality. Let's consider the probability paradox. The core idea behind quantum immortality is that in an infinite multiverse, any possible outcome, no matter how improbable, will occur in some timeline. This seems straightforward enough, but it leads to a rather unsettling conclusion. If every possible outcome occurs, then logically, an infinite number of outcomes must occur for every observer. Now, if that's the case, why do we experience a single, relatively consistent reality? Why aren't we constantly bombarded with bizarre and contradictory experiences, reflecting the infinite possibilities of the multiverse? The answer, proponents of quantum immortality argue, is that we only experience the timelines where we survive. But that doesn't explain why we experience a consistent timeline, rather than a chaotic jumble of improbable events. If every possible outcome occurs, then there should be timelines where the laws of physics are different, where history unfolded in radically different ways, and where our own identities are completely unrecognizable. Yet, we don't experience those timelines, at least not consistently. This suggests that there might be some underlying mechanism that filters out the improbable outcomes, or that our perception of reality is somehow biased towards consistency. One possible explanation is that our brains are wired to prioritize consistency. We tend to ignore or rationalize away contradictory experiences, creating a narrative that makes sense to us. This is a cognitive bias, but it might also be a necessary adaptation for survival. If we were constantly bombarded with random and contradictory information, we wouldn't be able to function effectively. Another possibility is that the many worlds interpretation is not entirely accurate. Perhaps the branching of timelines is not truly infinite, or that some timelines are more stable than others. This would mean that certain outcomes are more likely to occur than others, even in the multiverse. However, these explanations don't fully resolve the paradox. They simply shift the problem to a different level. Why would our brains be wired to prioritize consistency? Why would some timelines be more stable than others? The underlying question remains: how can we reconcile the infinite possibilities of the multiverse with the finite and consistent reality that we experience? Furthermore, consider the sheer scale of the multiverse. If there are truly an infinite number of timelines, then the vast majority of them will be radically different from our own and completely uninhabitable. They might be governed by different laws of physics, or they might simply be devoid of matter. In those timelines, there would be no observers to experience anything. This raises a question: why are we in a relatively hospitable timeline where life can flourish? Is it simply a matter of chance? Or is there some underlying principle that favors the existence of observers? This is known as the anthropic principle, and it's a controversial topic in cosmology. It suggests that the universe is fine-tuned for life, and that our very existence is a consequence of that fine-tuning. However, the anthropic principle doesn't necessarily explain why we experience a consistent reality. It simply suggests that we couldn't exist in a reality that was drastically different. The probability paradox remains a significant challenge to the concept of quantum immortality. It forces us to question our assumptions about the nature of reality and the role of consciousness in the universe. Let's begin by considering the possibility that our reality isn't, well, fundamentally real. The simulated reality hypothesis, popularized by thinkers like Nick Bostrom, proposes that we might be living within a computer simulation, potentially created by a vastly advanced civilization. This isn't simply science fiction, it's a serious philosophical consideration, with implications for our understanding of death and immortality. Think of it like a tremendously complex video game, one so realistic that its inhabitants, us, are unaware of its artificial nature. The key premise is that if a civilization reaches a point where it can create simulations indistinguishable from reality, the number of simulated realities would vastly outnumber the base's reality. Statistically, therefore, we are more likely to be within a simulation than in the original universe. If that's the case, what does death even mean? Does the simulation simply reboot us, or perhaps load a previous save point? Or maybe consciousness isn't tied to the physical body within the simulation and continues to exist as data even after the simulated body dies. It's a mind-bending concept, but it offers a different angle on immortality, one where death is merely a change of state within the program. Now, let's explore the implications for quantum immortality within a simulated reality. The many worlds interpretation, as we've discussed, suggests that every quantum event causes the universe to split into multiple branches. In a simulation, these branches might be computationally cheaper to represent as failures or errors from the perspective of the simulating civilization. But, from our perspective, those branches still exist. If our consciousness constantly shifts to the timeline where we survive, as quantum immortality proposes, and the simulation is sophisticated enough, it might correct any perceived anomalies to ensure our continued existence within the simulation. Think of it as a kind of automatic error correction. It doesn't necessarily mean we're invulnerable to all harm. Rather, the simulation subtly alters events to maintain our survival, perhaps by resolving dangerous situations just before they become fatal. This isn't about physical invincibility, it's about a persistent subjective experience of survival, mediated by the simulation itself. Furthermore, if the simulating civilization is benevolent, or simply doesn't care about individual deaths within the simulation, they might allow these survival biases to continue indefinitely, creating a form of digital immortality for those whose consciousnesses consistently navigate to survival timelines. However, there are challenges to this idea. One major concern is the computational cost of maintaining a detailed simulation, especially one that supports conscious beings. The resources needed to simulate even a single human brain, down to the quantum level, are astronomical. Some argue that this makes the simulated reality hypothesis practically impossible, but proponents suggest that the simulating civilization might employ shortcuts, simplifying aspects of the simulation that aren't directly relevant to the experience of conscious beings. This could involve reducing the fidelity of distant objects, or only rendering details when they are directly observed. Another challenge is the glitch in the matrix problem. If our reality is a simulation, we might expect to see occasional errors or inconsistencies. While some people point to unexplained phenomena as evidence of glitches, others argue that these can be explained by natural causes, or simply represent limitations in our understanding of the universe. Ultimately, the question of whether we live in a simulation remains open, but it provides a fascinating framework for exploring the nature of reality and the possibility of immortality. Let's shift gears and consider panpsychism. This is the philosophical view that consciousness, or something akin to it, is a fundamental and ubiquitous feature of the universe. It doesn't necessarily mean that rocks and trees are having complex thoughts, but rather that even the most basic particles possess some degree of subjective experience, however rudimentary. It's a departure from the traditional view that consciousness is an emergent property of complex systems like brains. Instead, panpsychism proposes that consciousness is a fundamental building block of reality, existing at all levels of existence. It's not necessarily about complex thought, but a simple, what it's like to be that particle. Some proponents argue that this solves the hard problem of consciousness, the difficulty of explaining how physical processes give rise to subjective experience, by simply asserting that experience is inherent in the physical world itself. Now, how does this relate to immortality? If consciousness is fundamental, it doesn't necessarily need a physical brain to exist. In other words, our consciousness isn't created by our brain, it's filtered through it. When our brain dies, the consciousness isn't extinguished. It simply no longer has a specific physical anchor. It could theoretically continue to exist in some other form, perhaps as a free-floating entity or as part of a larger universal consciousness. Within, this doesn't necessarily mean we'd retain our memories or personality, but the fundamental spark of consciousness might persist. It also ties into the idea of interconnectedness. If all things are conscious to some degree, there's a potential for a continuous flow of experience across the universe. death, in this view, isn't an ending, but a transition, a shift in perspective, or emerging with a larger cosmic consciousness. Of course, panpsychism faces its own challenges. One major criticism is that it's incredibly difficult to test empirically. How do you measure the consciousness of an electron? Another concern is the combination problem. How do individual units of consciousness combine to form the complex subjective experiences of conscious beings? Some proponents suggest that consciousness is integrated through quantum entanglement, while others propose that it's a result of information processing. Despite these challenges, panpsychism offers a compelling alternative to traditional materialistic views of consciousness, and it opens up intriguing possibilities for understanding immortality. If consciousness truly is fundamental, then death may not be the end of our experience, but simply a change in its form. Finally, let's consider the nature of time itself. Our everyday experience of time is linear. We perceive it as flowing from the past, through the present, and into the future. But this may be an illusion. Modern physics, particularly Einstein's theory of relativity, suggests that time is not absolute, but relative. It can be warped and stretched by gravity and velocity. And some physicists even propose that time is not a fundamental dimension at all, but an emergent property of the universe. The block universe theory, for example, suggests that all moments in time, past, present, and future, exist simultaneously. We simply perceive them sequentially due to the way our brains process information. If time isn't linear, then the concept of death becomes less definitive. It's not an ending point, but simply a different location within the block universe. This ties into our discussion of quantum immortality. If all moments in time exist simultaneously, then all possible timelines, including those where we survive, are equally real. Our consciousness, rather than moving linearly through time, might be sampling different timelines, constantly shifting to the one where we continue to exist. This isn't about predicting the future, but recognizing that all futures already exist. The sensation of flowing through time is merely a consequence of the way our brains construct a narrative from these simultaneous realities. We perceive a sequence of events, but that sequence is just one of many possibilities. And if our consciousness is not limited to a single timeline, then death, as a complete cessation of experience, becomes impossible. We simply continue to exist in another branch of the multiverse. The idea of a non-linear time also opens up possibilities for communication with the past or future, although this remains largely speculative. Some physicists propose that wormholes, hypothetical tunnels through space-time, could potentially allow for time travel, while others suggest that quantum entanglement could enable instantaneous communication across vast distances of time. Regardless of whether such phenomena are possible, the very concept of non-linear time challenges our fundamental assumptions about reality and offers a radical new perspective on the nature of existence. If time isn't what we think it is, then the boundaries of what's possible, including immortality, are far more expansive than we ever imagined. The true nature of time remains one of the greatest mysteries of the universe, but exploring its possibilities can offer profound insights into the nature of consciousness and the meaning of life. Let's begin by establishing what we mean by moral implications. In essence, we're exploring the rightness or wrongness of actions, particularly in light of the potential for indefinite survival, as proposed by the quantum immortality theory. Traditionally, morality often centers around minimizing harm and maximizing well-being. But what happens when death, the ultimate harm, is statistically improbable for the subjectively experiencing consciousness. Does that alter our ethical calculus? It certainly complicates it. We are accustomed to thinking in terms of finite lifespans, of consequences unfolding within a defined time frame. The notion of potentially enduring indefinitely challenges those assumptions. Consider a simple act like crossing the street. We assess the risk of being hit by a car. If quantum immortality holds true, in timelines where we are hit, our consciousness simply shifts to one where we weren't, avoiding that particular death. However, does knowing this lessen the importance of taking precautions? Some might argue it does, fostering a reckless attitude, while others might believe it amplifies responsibility, a duty to navigate timelines favorably. This is precisely what makes the ethics of survival so nuanced and fascinating. The core issue here isn't necessarily about avoiding death, but about the impact our actions have on other timelines and the beings within them. If our consciousness perpetually shifts to timelines where we survive, does that create a responsibility to those versions of ourselves who don't? Are we, in a sense, consuming their potential existences? This is a particularly thorny question. Many ethical frameworks emphasize minimizing harm to sentient beings. If we accept the many worlds interpretation of quantum mechanics, which underpins quantum immortality, then countless versions of ourselves do experience death in countless timelines. It becomes difficult to reconcile our subjective experience of continuous survival with the objective reality of widespread uses deaths elsewhere. It's a paradox that requires careful consideration. One way to approach this is to consider the concept of moral weight. If a timeline contains more suffering than another, might it be ethically justifiable, even necessary, to favor timelines with less suffering, even if it means sacrificing potential versions of ourselves? This gets into complex utilitarian calculations. Another consideration is the impact our survival has on resource allocation. If we indefinitely occupy resources that could otherwise benefit others, is that ethical? Let's further clarify the idea of moral weight as it relates to quantum immortality. In traditional ethics, we often weigh the consequences of our actions. If an action benefits 10 people but harms one, it's often considered morally justifiable. However, with quantum immortality, the number of people, or rather, versions of ourselves, becomes infinite. Every decision we make creates a branching point, spawning countless new timelines. This makes it extraordinarily difficult to assess the overall moral impact of our actions. Consider a scenario where you have a choice between two equally risky ventures. One venture has a higher potential reward, but also a slightly higher chance of catastrophic failure. In a traditional ethical framework, you might weigh the potential benefits against the potential harms. But with quantum immortality, if you fail, you simply shift to a timeline where you didn't, and the consequences of failure are effectively negated for you. However, what about the impact on others in that failed timeline? Do their experiences cease to matter? This is where the ethical complexities truly emerge. The challenge isn't simply about maximizing our own survival. It's about navigating a multiverse where our actions have potentially infinite consequences. Traditionally, the value of life is often linked to its finitude. The fact that our time is limited compels us to make the most of it, to cherish our relationships, and to pursue meaningful goals. But what happens when that finitude is removed, or at least significantly diminished? Does life become less valuable or more? This is a profound question that touches upon the very essence of what it means to be human. Some might argue that removing the threat of death diminishes the urgency of life, leading to apathy and existential ennui. If we know we can't truly lose, does that erode our motivation? Others might argue that it liberates us to pursue our passions without fear, to take risks and explore new possibilities. The absence of death could potentially unlock a level of creativity and innovation that is currently stifled by our awareness of mortality. It's also important to consider the subjective experience of life. Even if our consciousness persists indefinitely, does that guarantee a life of meaning and fulfillment? Or could it lead to an endless cycle of boredom and despair? The value of life isn't solely determined by its duration. It's also determined by the quality of our experiences and the connections we forge. If quantum immortality is true, it fundamentally alters our understanding of the relationship between risk and reward. Traditionally, we weigh the potential benefits of an action against the risk of death. But if death is statistically improbable for us, that calculation changes. We might be more inclined to take risks, to pursue ambitious goals, and to challenge conventional wisdom. However, this doesn't necessarily mean that life becomes careless. It simply means that our priorities shift. Instead of focusing solely on avoiding death, we might focus on maximizing our potential for growth, learning, and contribution. The value of life, in this context, becomes tied to our ability to create meaning and to leave a positive impact on the world. It's also important to consider the impact of indefinite survival on our relationships. If we outlive our loved ones, how do we cope with that loss? Do we become emotionally detached, or do we find new ways to connect with others? The challenge isn't simply about extending our lifespan, it's about maintaining the richness and depth of our human connections. Consider the concept of experiential wealth. In a finite life, we accumulate material possessions and achievements, but these ultimately lose their significance when we die. However, in an indefinite life, our experiences become our most valuable asset. The memories we create, the lessons we learn, and the relationships we forge become enduring treasures that transcend time. This suggests that the pursuit of meaning in an indefinite life should focus on cultivating rich and meaningful experiences. This might involve pursuing creative endeavors, traveling the world, engaging in lifelong learning, and fostering deep connections with others. It's also important to consider the role of purpose. Having a sense of purpose can provide meaning and direction in life, even in the face of adversity. In an indefinite life, our purpose might evolve over time as we learn and grow. The challenge isn't simply about finding a single, overarching purpose. It's about cultivating a flexible and adaptable mindset that allows us to embrace new opportunities and challenges. Experiential wealth, coupled with a sense of purpose, could potentially provide a fulfilling and meaningful existence, even in the absence of finitude. Suffering is an inescapable part of the human condition. It's often seen as a catalyst for growth, a teacher of resilience, and a source of empathy. But what happens to the meaning of suffering if death is statistically improbable? Does it diminish, or does it become more profound? This is a complex question that requires careful consideration. Traditionally, suffering is often seen as a temporary state, a challenge to be overcome. The knowledge that life is finite provides a sense of urgency and motivates us to make the most of our time. But if death is no longer a concern, does that diminish the importance of alleviating suffering? Some might argue that it does, leading to a sense of complacency and indifference. However, others might argue that it amplifies the importance of compassion and empathy. If we are capable of experiencing indefinite survival, we have a moral obligation to alleviate the suffering of others, to create a world where everyone has the opportunity to flourish. The meaning of suffering, in this context, becomes tied to our ability to transform pain into something meaningful, to use our experiences to help others, and to create a more just and compassionate world. If quantum immortality is true, it fundamentally alters our understanding of the relationship between pain and growth. Traditionally, we often see suffering as a necessary evil, a challenge that makes us stronger. But if we can avoid death, does that diminish the value of resilience? Some might argue that it does, leading to a sense of entitlement and fragility. However, others might argue that it amplifies the importance of inner strength. If we are capable of enduring indefinite survival, we have a moral obligation to cultivate our inner resilience, to develop the ability to cope with adversity, and to maintain our emotional well-being. The meaning of suffering, in this context, becomes tied to our ability to transform pain into wisdom, to learn from our mistakes, and to grow as individuals. It's also important to consider the role of empathy. If we are capable of experiencing indefinite survival, we have a moral obligation to connect with others, to understand their pain, and to offer them support. The meaning of suffering, in this context, becomes tied to our ability to create a community of compassion and understanding. Consider the concept of transformative suffering. Some experiences of suffering can be deeply transformative, leading to profound personal growth and a renewed sense of purpose. If quantum immortality is true, these experiences become even more valuable. The lessons we learn from suffering can endure indefinitely, shaping our character and influencing our actions. The meaning of suffering, in this context, becomes tied to our ability to integrate our experiences into our identity, to find meaning in adversity, and to live a life of purpose. It's also important to consider the role of forgiveness. Holding on to anger and resentment can be deeply damaging, both to ourselves and to others. If we are capable of experiencing indefinite survival, we have a moral obligation to cultivate forgiveness, to let go of the past, and to embrace the present. The meaning of suffering, in this context, becomes tied to our ability to heal, to grow, and to create a more compassionate world. Ultimately, the meaning of suffering is subjective and personal, but if quantum immortality is true, it becomes even more profound and enduring. Now, let's begin to gently explore where the quantum world touches the biological. For many years, quantum mechanics seemed confined to the realm of physicists studying very small, isolated systems. But increasing evidence suggests it's not merely a background effect. It actually plays a functional, crucial role in life itself. This is the field of quantum biology. It's a relatively new area, but incredibly exciting. The core idea is that certain biological processes aren't simply the result of classical chemistry and physics. They leverage quantum phenomena like superposition and entanglement to achieve efficiencies and capabilities that would be impossible otherwise. Think of it like this. Classical physics is like building with Lego bricks. You can make amazing things, but you're limited by the shape and properties of those bricks. Quantum mechanics is like having the ability to temporarily make those bricks exist in multiple states at once, or even be instantly connected across vast distances. That opens up possibilities that are, well, extraordinary. We aren't suggesting organisms are consciously harnessing quantum mechanics. but rather that these effects naturally arise from the way biological molecules are structured and interact. It's a subtle but important distinction. The question isn't, can life use quantum mechanics, but how does life already use quantum mechanics? One of the key concepts here is quantum coherence. This refers to the ability of a quantum system, like a molecule, to exist in multiple states simultaneously. Think of a coin spinning in the air. Before it lands, it's neither heads nor tails. It's in a superposition of both. Quantum coherence is fragile, easily disrupted by interactions with the environment. But, remarkably, some biological systems seem to maintain coherence for surprisingly long periods, even at relatively high temperatures. This is a major puzzle for physicists. How does life shield these delicate quantum states from environmental noise? Several mechanisms are being investigated, including specialized protein structures, vibrational modes, and the possibility of quantum entanglement. Entanglement, as you know, is when two particles become linked in such a way that they share the same fate, no matter how far apart they are. Some researchers believe entanglement may play a role in bird navigation, enzyme catalysis, and even consciousness itself. It's important to remember that these are all active areas of research. We don't have all the answers yet, but the evidence is mounting that quantum mechanics is far more pervasive in the living world than we previously thought. We'll delve into a couple of specific examples shortly to illustrate just how this might work. Another important quantum effect to consider is quantum tunneling. In classical physics, if you roll a ball at a hill, it needs enough energy to get over the top. If it doesn't, it rolls back down. But in the quantum world, there's a probability, even if it's small, that the ball could simply pass through the hill. This is quantum tunneling. It's a bizarre phenomenon, but it's been experimentally verified countless times, and it seems to be involved in several biological processes. For example, it's thought to play a role in enzyme catalysis, allowing enzymes to speed up reactions by tunneling electrons through energy barriers. It also may be involved in DNA mutations, where protons tunnel across hydrogen bonds, leading to errors in replication. While the probability of tunneling is low for any single event, over the vast timescale of life, these events can accumulate and have significant consequences. So even though it's a subtle effect, it could be a major driver of evolution. The implications are quite profound. These aren't just theoretical curiosities, they're potentially fundamental mechanisms that shape life as we know it. And, of course, they also add another layer of complexity to our understanding of quantum immortality. Remember, if quantum processes influence biological outcomes, then any timeline branching associated with those outcomes would be subject to the same quantum rules. Now, let's move on to a concrete example: photosynthesis. Let's consider photosynthesis, the process by which plants convert sunlight into energy. For decades, scientists have been puzzled by the remarkably high efficiency of energy transfer in this process. Plants capture sunlight using light harvesting complexes, which contain molecules called chlorophyll. These chlorophyll molecules absorb photons, particles of light, and then transfer that energy to a reaction center, where it's used to drive the production of sugars. Classical physics predicted that this energy transfer would be slow and inefficient, as energy would be lost due to vibrations and collisions. However, experiments have shown that the energy transfer is almost 100% efficient. How is this possible? The answer appears to lie in quantum coherence. The energy doesn't travel along a single defined path. It explores all possible paths simultaneously, thanks to quantum superposition. This allows the energy to find the most efficient route to the reaction center, bypassing obstacles and minimizing losses. Think of it like a maze. If you had to randomly try different paths, it would take a long time to find the exit. But if you could explore all paths simultaneously, you'd find the exit instantly. That's essentially what's happening in photosynthesis. Researchers have demonstrated this quantum coherence using sophisticated spectroscopic techniques. They've shown that the energy exists as a superposition of states, exploring multiple pathways before collapsing into a single efficient pathway. What's even more remarkable is that this coherence persists for surprisingly long periods, despite the warm, wet, and chaotic environment inside a plant cell. This suggests that plants have evolved mechanisms to protect this delicate quantum state. Some researchers believe that the structure of the light harvesting complexes, which are highly organized and symmetrical, plays a crucial role in maintaining coherence. Others suggest that vibrational modes within the molecules help to shield the quantum state from environmental noise. Whatever the mechanism, it's clear that quantum mechanics is essential for the efficient operation of photosynthesis. Without it, life as we know it would be impossible. And this isn't just a theoretical curiosity, it has practical implications. Understanding how plants harness quantum mechanics could inspire the development of more efficient solar energy technologies. If we could mimic the way plants capture and transfer energy, we could create solar cells that are far more efficient than anything we have today. It's important to remember that quantum effects aren't always about making things faster. Sometimes, they're about finding the most efficient path, even if it's not the fastest. In the case of photosynthesis, quantum coherence allows the energy to avoid getting trapped in local minima, energy valleys that would normally slow down the transfer. By exploring all possible paths simultaneously, the energy can bypass these obstacles and find the lowest overall energy pathway. This is a subtle but important distinction. It's not just about speed, it's about optimization. And this principle applies to many other biological processes as well. Now, let's turn our attention to another example: enzyme activity. Enzymes are biological catalysts, molecules that speed up chemical reactions. They do this by lowering the activation energy, the energy required to start a reaction. One of the ways enzymes achieve this is through a process called quantum tunneling. As we discussed earlier, quantum tunneling allows particles to pass through energy barriers that they classically shouldn't be able to. In the case of enzymes, protons, positively charged particles, can tunnel through energy barriers, speeding up the rate of reaction. This tunneling effect is particularly important for enzymes that catalyze reactions involving the transfer of protons. Researchers have found that enzymes are often structured in a way that maximizes the probability of tunneling. For example, they may create a narrow, confined space that allows protons to tunnel more easily. They may also vibrate at specific frequencies that enhance the tunneling effect. Experiments have shown that if you disable quantum tunneling in an enzyme, the reaction rate slows down significantly. This provides strong evidence that tunneling is not just a minor effect, it's an essential part of the enzyme's mechanism. Furthermore, some enzymes appear to be able to exploit quantum entanglement to enhance their catalytic activity. Researchers have proposed that entanglement between different parts of the enzyme molecule can create a more efficient pathway for the reaction. While this is still a relatively new area of research, the evidence is mounting that quantum mechanics plays a crucial role in enzyme catalysis. It's not just about lowering the activation energy, it's about finding the most efficient pathway for the reaction, leveraging the unique properties of quantum mechanics. This has implications not only for our understanding of biology, but also for the development of new drugs and therapies. If we can understand how enzymes harness quantum mechanics, we may be able to design drugs that are more effective and have fewer side effects. In conclusion, the evidence is mounting that quantum mechanics is far more pervasive in the living world than we previously thought. From photosynthesis to enzyme activity, quantum effects appear to play a crucial role in many biological processes. While we don't fully understand how these effects work, it's clear that they're not just theoretical curiosities. They're essential for life as we know it. And, as we've discussed, these quantum processes have implications for our understanding of quantum immortality. Any timeline branching associated with these quantum events would be subject to the same quantum rules, potentially creating multiple, parallel realities. This is a fascinating and complex field, and we're only just beginning to scratch the surface of its potential. As we continue to explore the intersection of quantum mechanics and biology, we're sure to uncover even more surprising and profound insights. Let's begin by unpacking the observer effect. It's a cornerstone concept in quantum mechanics, and often misunderstood. The basic idea isn't that simply looking at something changes it in a magical way, but rather that the act of measurement inherently disturbs the system being measured. In the quantum realm, things aren't neatly defined until they're measured. Before measurement, particles exist in a superposition, a blend of all possible states. Imagine a spinning coin in the air. It's neither heads nor tails until it lands. A quantum particle is similar. It exists in a probabilistic cloud of possibilities. When we try to pinpoint its state, its position or momentum, we force it to choose a single state. The interaction required to make that measurement, whether it's bouncing a photon off the particle or using any other measuring device, inevitably alters its original state. It's not about conscious observation, but about physical interaction. Think of trying to measure the air pressure in a tire with a gauge. The act of connecting the gauge releases a tiny amount of air, slightly changing the pressure you're trying to measure. That disturbance, even on a small scale, is the essence of the observer effect. This effect is crucial when considering quantum immortality because the measurement that collapses the wave function could be tied to conscious experience. Now, let's delve a little deeper into what constitutes measurement in this context. It's not necessarily a conscious being with eyes gazing upon a particle. Any interaction that correlates the quantum system with a macroscopic classical system qualifies as a measurement. Think of a detector clicking when a particle hits it. The detector itself is a macroscopic object, and the click is a classical event. This interaction creates a definite record of the particle's state, effectively collapsing its wave function. The wave function is a mathematical description of the probability of finding a particle in a certain state. When the wave function collapses, we get a single definite outcome. Importantly, this isn't just about the physical act of measurement. It's about the creation of information. The information about the particle's state becomes encoded in the measuring device, and that's what defines the measurement. This is why the role of observation, specifically in relation to consciousness, is so debated. If information is key, and consciousness is arguably a process of information processing, then could consciousness itself be a form of measurement? That is a question we'll circle back to later. The standard interpretation doesn't require consciousness, but it doesn't necessarily exclude it either. The key takeaway is that measurement is about interaction and information transfer, not just looking. Let's consider the double-slit experiment as a prime example. When particles are fired at a screen with two slits, they create an interference pattern, suggesting they're behaving like waves. This happens even if they're sent through one at a time. But if we try to observe which slit each particle goes through, by placing a detector near one of the slits, the interference pattern disappears. The particles now behave like discrete particles, going through one slit or the other. The act of observing, of measuring which slit they go through, forces them to choose a definite path, destroying the wave-like behavior. It's as if the particles know they're being watched. Of course, it's not about conscious awareness. The detector is simply interacting with the particles, providing information about their path. This interaction is enough to collapse the wave function and change the outcome. This experiment beautifully illustrates how the act of measurement, any interaction that gains information about the system, fundamentally alters the quantum reality. It's a principle that underpins much of the discussion around quantum immortality and the potential for multiple realities. Now, let's explore the quantum Zeno effect, which takes the observer effect to a fascinating extreme. It's often described using the analogy of Saint Zeno, who would repeatedly observe an arrow in flight, effectively freezing it in mid-air, because each observation prevented it from reaching its target. While the analogy isn't perfect, it captures the core idea. The quantum Zeno effect states that frequent measurements of a quantum system can actually prevent it from changing its state. Essentially, by constantly observing the system, you freeze it in its initial state. It's counterintuitive, but it's a well-established phenomenon in quantum mechanics. The more frequently you measure, the less likely the system is to evolve. This isn't about stopping the natural processes of the universe. It's about continually resetting the system to its initial state before it has a chance to change significantly. The mathematical explanation involves the probabilities of quantum evolution. Every quantum system has a certain probability of transitioning from one state to another over a given time period. But each measurement resets the clock, essentially restarting the probability calculation. If you measure frequently enough, the probability of the system changing state becomes vanishingly small. Think of it like flipping a coin repeatedly, but each time you flip it, you immediately look at the result and then reset the coin to its initial state. If you do this extremely quickly, the coin will effectively remain in the same state indefinitely. This is not to say it is impossible for the system to change, only that the probability of change is significantly reduced by frequent observation. This effect has practical applications in some areas of quantum computing and physics, but it's also deeply relevant to our discussion of quantum immortality. If constant observation can freeze a quantum system, could consciousness, as a continuous form of observation, play a role in stabilizing our reality? The implications of the quantum Zeno effect for quantum immortality are intriguing. If our conscious experience acts as a continuous form of measurement, could it potentially stabilize our wave function and prevent us from experiencing death? This is a central tenet of some interpretations of quantum immortality. The idea is that every time a life-threatening event occurs, our consciousness measures our state, preventing the wave function from collapsing into a state where we are deceased. Instead, the universe splits into multiple branches, and our consciousness continues to exist in the branch where we survive. This isn't about immortality in the traditional sense. It's about ensuring that there's always a timeline where we continue to experience subjective reality. However, it's crucial to remember that this is a highly speculative idea, and there's no definitive evidence to support it. It's a thought experiment that pushes the boundaries of our understanding of quantum mechanics and consciousness. Now, let's address the most challenging question. What role, if any, does consciousness play in all of this? The standard interpretation of quantum mechanics doesn't require consciousness for wave function collapse. Measurement, as we've discussed, is about physical interaction and information transfer, not about a conscious observer. However, some interpretations, like the von Neumann-Wigner interpretation, propose that it is consciousness itself that collapses the wave function. This is a controversial idea, and it's not widely accepted by physicists, but it remains a fascinating area of debate. The argument is that objective reality only comes into existence when it is observed by a conscious being. Before that, the universe exists in a superposition of possibilities, and it's consciousness that selects a single reality. If consciousness is indeed involved in wave function collapse, then it has profound implications for quantum immortality. It suggests that our subjective experience isn't just a passive observer of reality, it's an active participant in creating it. Every time we face a potentially fatal situation, our consciousness measures our state, preventing the wave function from collapsing into a state where we are deceased. Instead, the universe splits into multiple branches, and our consciousness continues to exist in the branch where we survive. This isn't about defying the laws of physics, it's about understanding that consciousness is an integral part of those laws. This interpretation implies that our survival isn't just a matter of chance, it's a consequence of the fundamental nature of reality. It's a bold claim, and it requires a radical shift in our understanding of consciousness and the universe. It's important to acknowledge that the connection between consciousness and quantum mechanics remains largely speculative. There's no conclusive evidence to support the idea that consciousness plays a fundamental role in wave function collapse. However, the exploration of this connection can lead to new insights into the nature of reality and our place within it. Whether or not consciousness is truly involved in shaping the quantum world, the very act of contemplating this question forces us to confront the deepest mysteries of existence. The discussion around quantum immortality, therefore, isn't just about the possibility of surviving death. It's about pushing the boundaries of our understanding of consciousness, reality, and the universe itself. The implications are far-reaching and challenge us to reconsider everything we thought we knew about the nature of existence. Let's begin with near-death experiences, often abbreviated as NDEs. These are profoundly subjective experiences reported by individuals who have come close to death, or believe they have. It's important to approach these with both scientific curiosity and respectful acknowledgement of the deeply personal nature of the accounts. Typically, NDEs involve a sensation of detachment from the body, a feeling of profound peace, seeing a bright light, and sometimes encountering deceased loved ones. What's fascinating is the consistency of these elements across vastly different cultures and belief systems. While many dismiss them as hallucinations caused by a dying brain, the complexity and consistency of the accounts push us to consider whether there's something more at play. One prominent theory suggests a surge of endorphins and oxygen deprivation can induce these visions. However, some individuals recall remarkably detailed experiences while clinically dead, meaning no measurable brain activity. This creates a fascinating conundrum for purely materialistic explanations. The question isn't necessarily did this actually happen, but rather, what does it tell us about the nature of consciousness and its potential independence from the physical body? The out-of-body experience, or OBE, is frequently a core component of NDEs. Individuals often describe watching medical personnel attempt to revive them, recounting details that could not have been known through normal sensory means. This is where things get particularly interesting when we consider the implications for quantum immortality. If consciousness can detach from the body, even temporarily, What prevents it from continuing to exist even after the body ceases to function? The key concept here is observation. In quantum mechanics, observation plays a crucial role in determining reality. If consciousness is fundamental and capable of existing independently, then every possible outcome of a quantum event, including survival, continues to exist in some branching timeline. This doesn't mean everyone survives indefinitely. It means you, the conscious observer, experience the timeline where you do survive. The NDE, then, could be a brief glimpse into this multi-timeline reality, a confirmation that your consciousness hasn't simply ceased to exist. Of course, this is speculative, but it provides a compelling framework for understanding these experiences within the context of quantum immortality. Let's consider the neurological side, however. Studies have shown increased activity in certain brain regions during NDEs, particularly the temporoparietal junction. This area is associated with self-awareness and spatial orientation. Some researchers propose that NDEs are caused by disruptions in this region, leading to the sensation of being outside one's body and experiencing altered perceptions of time and space. This explanation isn't necessarily incompatible with quantum immortality. It's possible the brain, in its final moments, is simply accessing or interpreting information from other timelines, projecting those experiences into conscious awareness. The brain could be acting as a receiver, tuning into the multitude of possibilities that exist within the quantum realm. It's also worth noting that the brain's activity doesn't prove the experience is illusory. It merely demonstrates how the experience is being processed. The subjective quality of the experience, the feelings of peace, love, and connection, remain unexplained by purely neurological accounts. Out-of-body experiences, or OBEs, aren't limited to near-death scenarios. Many individuals report intentionally inducing OBEs through techniques like meditation, lucid dreaming, or astral projection. This suggests that the ability to separate consciousness from the body isn't necessarily a product of trauma or dying, but a potentially innate human capacity. The experience typically involves a feeling of floating outside one's physical form, often with the ability to perceive the surrounding environment from a different perspective. OBEs can vary greatly in vividness and control. Some individuals report being able to move freely, travel to distant locations, and even interact with other entities. Others experience a more passive detachment, simply observing their surroundings without the ability to influence them. What's significant is that these experiences often feel incredibly real to the individual experiencing them, even indistinguishable from waking reality. From a metaphysical standpoint, OBEs suggest that consciousness isn't solely contained within the physical brain. If consciousness can operate independently, even temporarily, it implies that it exists as a fundamental aspect of reality, not merely a byproduct of brain activity. This aligns with the idea that consciousness is a field, a universal substrate that permeates all things. The brain, then, isn't the source of consciousness, but rather a receiver or antenna, tuning into this universal field. During an OBE, the connection to the physical body weakens, allowing consciousness to explore other realms or dimensions. This doesn't necessarily imply the existence of spirits or supernatural entities, but rather that there are other levels of reality beyond our normal sensory perception. Quantum mechanics supports this idea by suggesting that reality isn't fixed and absolute, but probabilistic and multidimensional. Now, let's think about the implications for quantum immortality. If consciousness is a quantum phenomenon, capable of existing in multiple states simultaneously, then every OBE could be a momentary shift into another timeline. Each time you have an OBE, you're essentially exploring a different branch of reality, a different possible outcome of your life. This explains why OBEs can sometimes feel so strange and disorienting. You're experiencing a reality that isn't your default timeline. It also suggests that the more you practice techniques that induce OBEs, the more you're potentially expanding your awareness of these other timelines, increasing your chances of shifting into a more favorable reality. It's important to note that this doesn't mean you can simply choose your reality. The laws of quantum mechanics still apply, and your actions and choices will continue to shape your experience. However, by expanding your awareness and exploring other possibilities, you may be able to increase your chances of surviving and thriving in any given timeline. All these experiences, NDEs and OBEs, force us to confront the fundamental question: what is reality? Classical physics portrays reality as objective, fixed, and independent of the observer. However, quantum mechanics challenges this notion, suggesting that reality is probabilistic, observer-dependent, and potentially multidimensional. The act of observation fundamentally alters the system being observed, collapsing the wave function and determining the outcome. This implies that consciousness isn't merely a passive observer of reality, but an active participant in its creation. If consciousness shapes reality, then it stands to reason that consciousness exists beyond the confines of the physical brain, perhaps as a fundamental aspect of the universe itself. The holographic principle, a concept originating from black hole physics, suggests that the entire universe can be thought of as a hologram, where information about three-dimensional space is encoded on a two-dimensional surface. This implies that our perception of reality is a projection, an illusion created by the interaction of consciousness with this underlying information field. If reality is a hologram, then it's possible that other realities exist within the same information field, accessible through altered states of consciousness or quantum phenomena. NDEs and OBEs could be glimpses into these other realities, moments where our consciousness breaks free from the limitations of our normal perception. Ultimately, the question of reality is a deeply philosophical one, and may never be fully answered. However, by exploring these altered states of consciousness and considering the implications of quantum mechanics, we can begin to expand our understanding of what it means to be conscious and what it means to exist. The concept of quantum immortality isn't about escaping death, but about recognizing the fundamental nature of consciousness and its potential to transcend the limitations of the physical body. It's about acknowledging that every possible outcome exists, and that you, as a conscious observer, continue to experience the timeline where you survive. And, perhaps, the journey of exploring these concepts is just as important as the destination. Now, let's address the elephant in the room: proof. Quantum immortality, as we've discussed, is largely theoretical. Bridging that gap to empirical verification is a monumental challenge. The core difficulty lies in the very nature of the hypothesis. It's self-confirming for the observer. If you die in a branch, you simply don't experience it. Therefore, traditional experiential designs, which rely on observing outcomes, fall short. One proposed approach, though fraught with ethical and practical hurdles, involves utilizing highly sensitive brain activity monitoring during near-death experiences. The idea isn't to cause near-death experiences, but to observe if there's any detectable continuation of consciousness, a flicker, even when all physiological signs of life cease. This requires technology capable of detecting incredibly subtle neural signals amidst complete bodily shutdown and discerning them from noise. It's akin to listening for a whisper in a hurricane. A significant problem is distinguishing between actual continued consciousness and residual brain activity, the echo of dying neurons. We'd need to establish a clear baseline of normal dying brain activity and then demonstrate consistent anomalies only in individuals who, theoretically, are shifting to another branch. Another promising avenue is exploring the many worlds interpretation using quantum computing. If we could create a quantum system complex enough to mimic branching realities, and then somehow probe those branches, which is a massive if, we might be able to gather indirect evidence supporting the existence of multiple timelines. This is well beyond our current technological capabilities, but it's a direction some researchers are exploring. Let's delve a little deeper into the quantum computing approach. The core idea isn't to see other timelines directly, but to observe the statistical distribution of outcomes in a highly complex quantum system. If the many worlds interpretation is correct, and every quantum measurement causes the universe to split, then the probabilities of different outcomes should reflect the weight of each branch. Think of it like a river delta. The main channel represents the most probable outcome, while smaller tributaries represent less likely ones. If we could accurately measure the flow of probability across all branches, we might be able to detect deviations from what classical probability theory predicts. These deviations could be interpreted as evidence for branching realities. However, there's a significant challenge here: decoherence. Quantum systems are incredibly fragile, and any interaction with the environment can cause them to lose their quantum properties and collapse into a single state. Maintaining quantum coherence long enough to perform meaningful measurements is a major technical hurdle. Furthermore, even if we could detect deviations from classical probability, it wouldn't necessarily prove the many worlds interpretation. Other interpretations of quantum mechanics could also explain the same observations. Therefore, any experimental evidence would need to be carefully analyzed and interpreted in light of all available theoretical frameworks. The goal isn't to prove quantum immortality definitively, but to gather evidence that makes the many worlds interpretation, and by extension, the possibility of quantum immortality, more plausible. Beyond experimental verification, substantial theoretical work is needed. Currently, much of the discussion around quantum immortality relies on intuitive explanations of the many worlds interpretation. We need a more rigorous mathematical framework to describe the process of subjective experience across branching timelines. How does consciousness select a particular branch? What determines the probability weighting of each branch from the perspective of the observer? These are incredibly difficult questions that require a deeper understanding of the relationship between consciousness, quantum mechanics, and information theory. One promising avenue is exploring the concept of quantum information. If consciousness is fundamentally a quantum phenomenon, which some theorists believe, then it might be encoded in quantum states. This would mean that when the universe branches, the quantum state of consciousness is also duplicated across multiple timelines. The challenge is to understand how this duplication occurs and how it affects subjective experience. Another important area of research is exploring the implications of different interpretations of quantum mechanics. While the many worlds interpretation is the most commonly invoked in discussions of quantum immortality, other interpretations, such as Bohmian mechanics or objective collapse theories, could also have implications for our understanding of consciousness and survival. Each interpretation offers a different perspective on the nature of reality and the role of the observer, and each could lead to different predictions about the fate of consciousness after death. Let's consider the role of information more deeply. If we accept that consciousness is fundamentally informational, meaning that it arises from the processing of information, then we can begin to explore how information is preserved across branching timelines. In a many-world scenario, every quantum measurement creates a new universe, but it also creates a new copy of all the information contained within that universe. This raises the question, is this information perfectly preserved, or is there some loss or distortion? If information is lost, then our subjective experience might not be continuous across timelines. We might experience gaps or discontinuities in our awareness. However, if information is perfectly preserved, then our subjective experience might be remarkably smooth and seamless. One way to investigate this is to develop a mathematical model of subjective experience that incorporates quantum information theory. This model would need to account for the following factors: the quantum state of the observer, the environmental interactions that affect that state, and the process of branching that creates multiple timelines. It's an immensely complex undertaking, but it could potentially shed light on the nature of consciousness and the possibility of quantum immortality. Furthermore, exploring the connection between consciousness and quantum entanglement might offer a new perspective on the preservation of information across timelines. If consciousness is entangled with multiple universes, then it might be possible to transmit information between them, ensuring the continuity of subjective experience. Now, let's move beyond the theoretical and consider the potential technological implications. If quantum immortality is even remotely plausible, it could revolutionize several fields. The most obvious is medicine. If we can understand how consciousness persists across branching timelines, we might be able to develop technologies that extend lifespan or even achieve a form of digital immortality. Imagine a future where your consciousness can be uploaded to a quantum computer and preserved indefinitely, allowing you to continue experiencing reality even after your physical body has died. Of course, this raises a host of ethical and philosophical questions, but it's a fascinating possibility to consider. Another potential application is in the field of artificial intelligence. If we can create AI systems that are based on quantum principles, we might be able to create machines that are truly conscious and self-aware. This could lead to the development of AI assistants that are capable of understanding and responding to our needs in a way that is currently unimaginable. However, it also raises concerns about the potential risks of creating AI that is more intelligent than humans. Beyond medicine and AI, the implications for communication and data storage are profound. Imagine a future where information can be transmitted instantaneously across multiple universes, allowing us to communicate with loved ones who have passed away, or even with alternate versions of ourselves in different timelines. This would require the development of quantum communication technologies that are far beyond our current capabilities, but it's not entirely beyond the realm of possibility. Furthermore, the ability to store information in multiple universes would provide an unprecedented level of security and redundancy. Even if one universe were to be destroyed, our data would still be safe and accessible in another. However, it's important to acknowledge that these technologies also pose significant risks. The potential for misuse is enormous, and we need to carefully consider the ethical implications before pursuing them. For example, the ability to manipulate timelines could have disastrous consequences, and we need to ensure that such technologies are used responsibly. Ultimately, the pursuit of quantum immortality is not just a scientific endeavor, it's a philosophical one. It forces us to confront fundamental questions about the nature of reality, consciousness, and our place in the universe, and that perhaps is its most important contribution. We've journeyed through a fascinating and admittedly quite strange landscape. Let's recap the core ideas underpinning the concept of quantum immortality. At its heart, this isn't about achieving physical invincibility. It's a consequence of the many worlds interpretation of quantum mechanics, which proposes that every quantum event causes the universe to split into multiple universes, each representing a possible outcome. Think of it like a branching tree, constantly expanding. Now, when faced with a life-threatening event, quantum mechanics dictates there's a probability, however small, that you'll survive. In at least one of those branching universes, you do survive. Crucially, your consciousness continues to experience reality from the perspective of that surviving timeline. It's not that you avoid death, but rather that your subjective experience simply shifts to a universe where you didn't die. We've explored how this differs from traditional ideas of immortality, emphasizing that it is a subjective, experience-based phenomenon, not a guarantee of perpetual physical existence. Remember, many versions of you will experience death, but you, the conscious observer, continue along the path of survival. A key component is the idea of subjective continuity. Our consciousness isn't tied to a specific physical body, but to a stream of experience. As long as that stream continues, you continue to exist, albeit in a potentially very different universe. This doesn't mean there's some magical transfer of consciousness. It simply means that your awareness follows the timeline where you continue to perceive. It's vital to remember, we are not positing a soul or spirit. It's a natural consequence of the physics, if the many worlds interpretation is correct. Consider a coin flip. In one universe it lands heads, in another tails. Both outcomes are equally real. Similarly, in universes where you face a deadly situation, there's a universe where you overcome it. And because your consciousness can only experience what it experiences, it follows the surviving path. It's a subtle yet profound shift in perspective, moving away from thinking about you as a fixed entity and more as a pattern of experience following the most probable, or rather, the continuing timeline. Let's pause and consider the philosophical implications of all this. The concept of quantum immortality, even if purely theoretical, challenges our traditional understanding of death. We often view death as a finality, an absolute end to consciousness. But if our consciousness simply shifts to a surviving timeline, then death becomes more of a transition, a branching point. It doesn't negate the sadness or loss associated with the death of others in different timelines. Their experiences remain real and significant, but it alters our perspective on our own fate. It's important to avoid interpreting this as a justification for reckless behavior. While the theory suggests your consciousness will continue along a surviving path, the universes where you survive may be drastically different and potentially undesirable compared to the one you currently inhabit. The you who survives might face profound challenges or live a life vastly unlike the one you envision. Furthermore, it forces us to confront the nature of self. Are we defined by our physical bodies, our memories, or our continuous stream of experience? Quantum immortality suggests the latter. The you who survives isn't necessarily the same you who started. Your memories may diverge, your personality may evolve, but the continuity of experience is what defines your ongoing existence. It's a humbling thought, recognizing that our sense of self is fluid and adaptable, constantly shaped by the unfolding of events across countless universes. it also prompts questions about meaning and purpose. If consciousness continues indefinitely, what motivates our actions? Does the potential for infinite survival diminish the value of individual moments? These are complex questions with no easy answers, and the exploration of quantum immortality is as much a philosophical exercise as it is a scientific one. Importantly, it's crucial to avoid misinterpreting quantum immortality as a promise of a perfect afterlife. The surviving timelines aren't necessarily utopian. You might find yourself in universes where things are far worse than your current reality. Survival doesn't equate to happiness or fulfillment. It simply means your conscious experience continues, potentially in a vastly altered and challenging environment. It's a nuanced perspective, demanding a rejection of simplistic notions of immortality and a willingness to embrace the complexity of existence. The universe, according to this interpretation, isn't concerned with our well-being. It simply unfolds according to the laws of physics, and consciousness follows the path of least resistance, or rather, the path of continued experience. Looking ahead, what does the concept of quantum immortality suggest about the future of consciousness? If our consciousness is fundamentally linked to the unfolding of quantum events, then understanding the nature of consciousness may require a deeper understanding of quantum mechanics itself. Perhaps future technologies could even allow us to manipulate quantum events in ways that enhance the probability of survival in certain timelines, though this remains firmly in the realm of speculation. It's also possible that consciousness isn't limited to biological organisms. If consciousness is a fundamental aspect of the universe, then it may exist in other forms, in artificial intelligence, in quantum systems, or even in the structure of the universe itself. The exploration of quantum immortality serves as a reminder that our understanding of reality is incomplete. We operate with limited perspectives, bound by our biological limitations and cognitive biases. The universe may be far stranger and more complex than we can currently imagine. The concept encourages us to embrace curiosity, challenge assumptions, and remain open to the possibility of extraordinary phenomena. It also highlights the importance of ethical considerations. If we ever gain the ability to manipulate timelines or influence the fate of consciousness, we must do so with caution and responsibility. The potential consequences of such power are immense. Ultimately, the journey through quantum immortality isn't about finding definitive answers. It's about asking profound questions, expanding our understanding of reality, and appreciating the mystery of existence. It's a thought experiment that forces us to confront our own mortality, reevaluate our priorities, and embrace the beauty and fragility of life. And perhaps, just perhaps, it offers a glimmer of hope, a suggestion that consciousness, in some form, may endure beyond the limitations of our physical existence. The universe is vast, mysterious, and full of possibilities, and the exploration of quantum immortality is merely one small step towards unraveling its secrets.